Good morning, class. Today we are looking at synchronous sequential circuits design. We have seen that slide before. We've looked at analysis, where in the analysis you are given a circuit diagram, you look at the flip-flop input equations, then you derive your output state and transition tables, you reduce it. We haven't done that. That is optimization. And then you get the state table, state diagram, and describe. Design is the opposite. You are given a verbal description of a problem that you need to design. You have to reason out and obtain the state table, which is the same as the state diagram, and then get the output and state transition table, flip-flop input equations, and then get the circuit diagram. So welcome. We will look at the steps of synchronous finite state machine design. So you need to carefully obtain the specifications of the desired circuit. You need to create a state diagram from the specifications. To me, this is the most important task. Understand the problem, create a state diagram. Then you can create a state table from the state diagram. In some cases like counters, it is easier to go straight to the table without a diagram. Then perform state minimization. These are optimization techniques that we will look at in the next topic. Determine the number of state variables. This will give you the flip-flops that you will use. Perform state assignment, still optimization. We will look at that in the next topic. Obtain the binary coded state table. Choose the type of flip-flops you want to implement your circuit and use the excitation table, and derive, simplify your circuit. You need to make it cheaper, and then you draw your logic diagram. So let's start with sequence detectors, the design of sequence detectors. So design a circuit that detects 3 or more consecutive ones in a string of bits coming through an input line. The first step is understand your problem. You've got an input line, you've got an output line, and you've got your system, control systems. Bits are coming in serially, one by one. When you detect a sequence of 3 or more consecutive ones, your output should be high. It should be low otherwise. So understand the problem and get the specifications. That is your input X, your output Z, your clock. And then you need to actually ask yourself, what type of machine do I want to design? And then you determine the states and draw a state diagram. So in understanding the problem, let's look at these sequences. That is what is coming in X0, 0, 1, 1, 1, 1, 0, 1, 1. When is Z1? And for what type of machine? So we've got two machines here. So 0Z should be 0, 0Z should be 0, 1, that's the first one, second one, third one, there should be a 1 there or there, fourth one, there should be a 1 here or there, depending on the type of machine. So if it is a more milli machine, once this one comes, the output becomes 1. If it is a more machine, it will start 1 at the next clock cycle. So those are the differences between milli and more machine. You can see one is faster and the other one is slower. So the most important thing is deriving the state diagram. We should start by understanding what the state means. What will you keep in memory this time? Ask that question in class. What do you keep in memory? You should keep in memory the number of ones that have arrived. So you have state S0 is 0 ones detected. You can look at it as a reset state. You haven't received the 1. S1, you have received the first one detected. S2, 2 ones, the second one detected. S3, the third one detected, and the output should be 1. If you detect another one, you cycle through that state with an output of 1. So from this, you should draw the state diagram. So that is the milli state diagram, and that is the more state diagram as discussed in class. S0 is there is no 1 detected. If 0 comes, you keep on there. If 1 comes, S1, the first one has been detected. If it's a 0, you break the cycle. If it is a 1, then the second one has been detected. Okay, if it is a 0, the cycle is broken. If it is a 1, the third one has been detected and the output is 1. If you are here in the 1, it means consecutive 1, so the output is 1. If a 0 comes, you break the cycle. When you are drawing this, always go to the required root 1 1 first, so you can convert this into that. Now, from a state diagram, you can easily get your state table. You have your present state input, next state output. If your present state is S0 and your input is 0, as we saw, the output will, the next state will be still S0 and the output will be 0. So you fill in that table. From there, should be basic. Then step 4, perform state minimization. We are not doing that. Then we need to determine the number of state variables. If you have 4 states, how many flip-flops do you need? 2 to the power of n, so you need 2 state variables for 2 flip-flops. So now, this is the table we had. The next step is perform state assignment. What binary value will you give the state? Remember, this will be done later. It's also just a topic on its own. For now, let's call S0 00, S1 01, S2 10, S3 11. So where you have S0, you replace it with 00, S0 there 00. Where you have S1 01, S0 00, S1 here 01, you get that table. Then you split that table. Call this column state A, that one B, next state of A and B. That is done there. A, B, X, next state A, B, Y. Split. It is in 2 flip-flop forms. It has been separated into two flip-flops. And then separate it further. You got the present state input, next state of A, present state input, next state of B, present state input, output. So you can do that. Split it further. And then after that, you need to decide the flip-flop you use and look for the excitation table. The excitation table gives you what should be at the input for the change in state. It is actually opposite of the first table we encountered, the truth table. So, for example, for a D flip-flop, if the present state is 0, the next state is 0, what should be at D is 0. For the JK flip-flop, the present state is 0, next state is 0, J should be 0, K should be X. For T flip-flop, if the present state is 0, next state is 0 should be in memory. For the SR should be 0X. These tables are given, but it's common sense. So, now, in those flip-flop tables, we add another column there for the flip-flop input equation for flip-flop A, input equation for flip-flop B. This is our excitation table. We are looking at a D flip-flop that gives us what should be at D for the transition from, in this case, 0 to 0, 0 to 1. Then ask yourself, if the present state of A is 0, and the next state is 0, what should be at A? The present state is 0, next state is 0, D should be 0. So we expect a 0 here. As a matter of fact, this column and this is the same. For D, the next state is what is at D input. So you can see those ones are the same. The same for this. Let me take another one here. If the present state is 1, the next state is 1, and what should be at D? Should be at 1. So you do that, you determine dA and B, and then you derive the equations, mean terms, max terms of dA in terms of ABX, dB in terms of ABX. So those are the equations below. After the equations, this is the output. You derive the equation of the output in terms of ABX, you get that equation. That is basically your design, but you need to minimize it. So to minimize it, we will use the Carnot maps, or you can use minimization equations. DA is plotted here. You've got ABX. So you get those ones, cover those, you minimize it into that. You do that for flip-flop B, and that is the minimized equation. You do that for Y, that is the minimized equation. Then from there, that is your design. You've got your DA. You should know an addition is an OR, this multiplication is an AND, complement is not. So then you are using D flip-flop, that is your DA, that is your DB, that is your AB. You can draw that circuit. In the exam, you don't need to draw the circuit. All that information is contained here if you don't have time. So on your own, implement the Mealy circuit. The design never changes. What changes is the question and how you get the state diagram. Otherwise, the procedures are the same, and from now on, we are going to look at examples. For example, design a synchronous sequential circuit with one input X and one output Z that recognizes the input sequence 0, 1 using a JK flip-flop. There is your input. If it is 0, 1, output should be 1, 0, 1, output 1, like that. We will skip some steps. What type of machine do you want to design? Determine the state. So what will be the state? State 0, 0 detected, state 1, 1 detected. You should have that state diagram. You should know how to derive that state diagram. And then from the state diagram, you've got your state table. That should be basic. State 0, 0, input is 0, you go to S0, output is that. So how many flip-flops? You've got 2 states, so you need only 1 flip-flop. Need 1 flip-flop, you've got 2 states. So state assignment is 0 is 0, S1 is 1. Then that is the excitation table. So you've got your A, your input, next state. You've got your Y. So you need to look for the JK inputs. Then ask yourself, is the present state is 0, the next state is 0, what should be at J and K? Present state 0, next state is 0, J should be 0, X, K should be X. That is what you expect to get here, 0, X. So fill in those. Then determine your equations. Those are the equations. Then minimize them with the K map. You've got AX there, you've got AX there, you've got that. If you minimize, you will get those equations, and if you draw your circuit, you get that simplified circuit that performs the task. So as we said, the design involves the same steps. What we are going to do is just looking at different examples. For today's lecture, we will stop there, and thanks. Welcome everybody to part B of synchronous sequential circuits design. We are continuing with our examples. We said the design process is the same, the procedure is the same, but we just need to introduce ourselves to more examples and learn how to derive the state diagram. So let's start with the parity checker. You are supposed to design an odd parity checker machine using a T flip-flop. You need to know what odd parity is. If the number of ones are odd, should return a 1. The assert output whenever input stream has odd number of ones. So the most important thing, as we said, what is the meaning of your state? Here, if you check carefully, you should determine whether you are in the even or odd state. If you are in this state, when the 1 comes, you go to the next. When the 0 comes, you remain there. So even state, we call it S0, odd state S1. So we'll use a state variable A for Mealy and B for more. We are going to design both states. So this is a Mealy machine. If you are in the even state and the 0 comes, you stay in the even, output is 0. If a 1 comes, the parity becomes odd, the output is a 1. If you are in the odd state and 0 comes, you will remain in the odd. So the parity is 1. If a 1 comes, you go to even, a parity is 0. So the same basically should be for the more machine. So I say the more machine, the output is associated with the present state, not next. The Mealy machine, the output is associated with the transition, appears before the state transition is completed by the next clock pulse. So from the state diagram, we can easily derive the state tables for milli and for more. Perform state assignment where S0 is 0, S1 is 1, we get those encoded state transition tables. Now we use the excitation tables to get the inputs to the flip-flop. We've got that present state input, next state T. If the present state is 0, next state is 0, what value of T should we have here? So present state is 0, next state is 0, T is 0, that is why we have that. It's in memory. If the present state is 0, the next state is 1. It means it toggled, so that should be 0, 1, it should be 1. So you can fill in that. Y still comes from our state diagram. That should be done for the more state. Then you get your equations, plot the Karnaugh map, simplify it, and you get your equations there. Simplified equations. From that, you can draw the milli machine is there. You can draw the more machine is there using the T flip-flop, and then you can even determine that if an input sequence is that and the clock is that, your output sequence will be that. You can be given a timing behavior type of question as well. Another example is design a D flip-flop using a JK flip-flop. What do you want? A D flip-flop. Do you need to have a state diagram? No. For a D flip-flop, you can go straight to a state table. We said in some cases, you can go straight to a state table. What do you want? You've got JK flip-flops. You want a D flip-flop. How do you do that? So the first thing is you have a table of a D flip-flop functionality, and there it is. When this is the present state, input at D, next state. You derive that from the functionality of a flip-flop, of a D flip-flop. Now we just need the inputs to J and K. So if the present state is 0 and the next state is 0, what should be at J and K? 0, 0. J should be 0, K should be don't K. That is what you expect to see, 0, don't K. So fill in those and then create your equation in the K maps. By the way, from here you can straight fill it in the K map if you don't want equations. Then when you minimize, you get J equals to DK equals D complement. So if you have a JK, you just need to have a NOT gate between J and K, and then you have a D flip-flop. Go through it and understand. Next, now assuming we've got D flip-flops and you want JK, what do? We start with the table of the behavior of the JK. That's present state J, K, in that. You have to get this from the behavior of JK. If they are 0, 0, it's in memory. 0, 1, reset. 1, 0, set. 1, 1, toggles like that. Once you get the next state, and then you use the excitation table to get D value. The D value will be the same as the next state. After that, you minimize and get your equation. So then you derive your JK from a D. Still with the examples. Now we go to counter designs. Design a counter that counts the following sequence: 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0. So here the state diagram is very easy. It's counting like that. The state table, binary encoded. Remember, there is no input, no output. Binary encoded state table, present state, next state, flip-flop inputs. We are using T flip-flop, T8, T0, T1, T2. From that, we get the T equations and then use the Karnaugh map to minimize. So the procedure is still the same. Then you will get TA is that, and that. So that is your circuit. You need to go through these examples on your own and make sure you master what is happening in the procedure. But as we said, the most important thing is the derivation of the state diagram and state table. Now you've got this. Design a sequential circuit with two JK flip-flops A and B, two inputs X and E. If E equals 0, the circuit remains in the same state regardless of the input X. When E is 1 and X is 1, the circuit goes through the state transition from 0, 0 to 0, 1 to 1, 0 to 1, 1, back to 0, 0, counts clockwise and then repeats. When E is 1, X is 0, the circuit goes through the state transition 0, 0, 1, 1, like that. Easy, you've got two inputs. So you have to draw the state diagram. It's drawn for you. You go through and see how we achieve that. Those are the two inputs. They are sometimes separated by a comma. So from that, count as normally the binary encoding is already there. You've been given A, B. Inputs are EX. Make sure you tell me the order of inputs. Next state is AB. Then your excitation, flip-flop excitation table gives you JAKA and JBKB. So you go to the kernel maps, minimize, and you will get your circuit as that. Go through these examples, understand properly. A counter with an arbitrary counter design, a sequence, doesn't mean that the counter should increment in steps of 1 or regular steps. This one counts 5, 7, 3, 2, 6 and repeats 5, 7, 3, arbitrary count sequence. You can design it. So you've got the current state and the next state. If the current state is 5, let's take an example. The next state is 7. This is just in binary. The current state is 7. The next state is 3. So you can easily get the current state, next state, no input. And then you can determine the flip-flop inputs. They are just a function of, they are just like the next state. Remember, the unused state 0, 0, 0, 0, 0, 1 go to don't cares. Doesn't matter, but we will deal with those later. So once you do that, you can minimize, Karnaugh map is there, and then get your final equation. That's a good design. But remember, you need to deal with the unused states. This is, let's look at the unused state. 0, 0, 0. If A is 0, if the present state is 0, 0, 0. If A is 0, B is 0, C is 0. What is at D? D is 1, because that is B complement, and 1, 1. So D will be 1, DA will be 1, DB will be 1, and 0 will be 1. DB will be 1, so we'll have 1, 1. And then DC will be, DC is a 0, 1, 1, 0. So if we had 0, 0, 0 here, this will be 1, 1, 0. So 1, 1, 0 is part of our sequence. We are safe. We are looking at that. We are saying you need to deal with the unused states and make sure, should they occur, they lead to a state in your sequence, a stable state. So we said if an unused state is 0, 0, 0, the next state will be 1, 1, 0. It will go through our counting sequence. Check 0, 0, 1, it will eventually get into a count sequence. 1, 0, 0, go there. If that is not the case, you will have to go back on the table. Instead of this don't cares, force it to go to a known sequence. Watch out for unused state. BCD counter, another example. Counts 0, 0, 0, 1 like that. Present state, next state, JAKA, JB, you know that. Go through these examples, same. Once we get that table, then the procedure remains the same. Those are your A maps and your equations. Of course, we won't bring such a long thing in the exam, but it can come in the assignment. And then deal with the unused states, and your circuit is that. So in summary, you should be able to design sequence detectors, flip-flop conversions, counters, and general finite state machines. We will deal with other examples as we continue. Thank you very much. Thanks.